So, good morning, my dear student. I welcome you in this last session of your course, that is the course number 9, unit 4, of course, second semester, and the topic is barrierless chemical reactions. Now, if you see my title, I have written a very old and conventional equation, and you all are aware of this equation, that is called Arrhenius equation, or you can call it effect of temperature. And basically, you have completed the whole first semester course as well as the second semester course regarding the molecular reaction dynamics, various chemical reactions. And if I ask you a very simple question, what is the effect of temperature on the chemical reactions? The answer is very simple, because long back Arrhenius proposed this thing, that rate of reaction increases. And there is a activation energy, or that is called from reactants to product, there is a barrier. But if you see the title, today I am going to discuss is a non-conventional system where there is no barrier. Is it possible? Yes, it is possible. So that is barrierless chemical reactions. Now what I am planning, that because it is a very broad subject and it is a completely research oriented subject, and you will not get complete information in a conventional textbook. But fortunately, there are a large number of good research papers available. So what I have done, I have collected large number of research papers and I have chosen some of the very simple reaction for the student, so you can understand what is actually barrierless chemical reactions. So there will be two lectures. In first lecture, I will not describe any mathematical or numerical derivation. Simply, I will explain some of the very popular barrierless chemical reactions. And in my second lecture, I will try to explain some of the equations related to, or you can call some of the models or the theories of the barrierless chemical reactions. Now, as you know that it comes under the molecular reaction dynamics, because most of the barrierless chemical reactions are very fast. So conventional method will be not very useful for studying this barrierless chemical reaction. Most of these are ultra fast laser spectroscopy is required to study the barrierless chemical reaction. So like my earlier chapters, when I dealt with the earlier chapters, I always referred this book edited by Professor Satyamurthy, Reaction Dynamics, Recent Advances by N. Satyamurthy. And there are many chapters because it is a edited book. But for this barrierless chemical reaction, I have chosen chapter number 5. And my most part of this lecture is based on this chapter written by a great scientist. Many times I have mentioned his name. He is Professor Biman Bagchi from M.Sc. Bangalore, and although it is not very new paper, but he has published large number of research papers on this barrierless chemical reactions, diffusion control reactions. So most of my lecture is based on this chapter. So please refer this book So I must acknowledge this research paper, and the title is also Dynamics of the Barrierless Chemical Reaction in the Solution. In addition to that, I have referred large number of old as well as the new research papers. But bear in mind, because you are all M.Sc first semester, second semester students, so I have chosen most simple example so that you can write in examination or internal assessment test. Okay. Now, as I told you that not only I have referred this old book Reaction Dynamics, but also I have referred some of the very good articles written by Professor Bakchi, like on the temperature dependence of the rate in barrierless chemical reactions, because that is the most important. What is the effect of temperature like that? How do you study the barrierless chemical reactions? Then, of course, some of my simple derivation is based on this one of the most important paper, Dynamics of the Activation-less Reactions. Barrierless, or you can call it is a activation-less. That means there is no barrier for the activated complex. If I plot a graph between the potential energy and the reaction coordinate, suppose it is reaction coordinate and potential energy, so it is normal, generally we call it. But here you will get different types of things, a whale-like things. There is no barrier, so therefore sometimes it is called the activation-less reaction. Barrier-less or activation-less reactions. Because in traditional picture, of course, there is a passage of the reactants to product, that is the activation barrier. Similarly, I have also referred some of the paper written by Bakchi and his collaborators. That is also very important. Sometimes what happened, if we study the barrierless chemical reactions in dispersive medium, most of the photoisomerization reaction, some of the electron transfer reactions. So basically we use the Brownian motion and a equation related to the Brownian motions. So it is also not very old paper, but Journal of Physical Chemistry 2008, of course Journal of Physical Chemistry B. Then again, there are some desk. I'll explain this curve, everything I'll explain, but this is the again the same paper of these things. Then you know that generally we believe that most of the theory was developed by Bakchi, but I have also gone through a very recent paper, not very recent, but 2018 by Aniruddha Chakrabarty. That is also a very new model. There is slight modification of that model. So in my second lecture, I'll also try to explain this recent model. Of course, he is a professor of IIT Mandi, so that model is also very good, but it is rather difficult model. Some for the student, not for the researcher. But somehow I will try to explain this model by a very simple method. Similarly, I have also chosen some of the very popular barrierless chemical reactions written by some American scientists and published in a very important journal, Journal of American Chemical Society. I'll explain all these things, the example of this type of the electron transfer reaction, so don't worry for that. I'm giving the very simple example. Then I have also referred this astrophysical journal, because most of the there is a subject that is called the astrochemistry, or some of the environmental type of the reactions, very fast reactions. So I'll also discuss this Ohno and Meda model also. Now coming by the first point, that If I again and again, many times I ask my students, and I think in my last lecture I also requested you to search your literature, search your smartphone, that is it possible or have you ever seen the negative activation energy? So your answer may be yes, your answer may be no. Because generally, how we get the negative activation energy? And if you see the simple Arrhenius model, so generally what happens that if we increase the temperature, the rate of reaction increases. And basically the temperature coefficient may be 2 or 3 like that. And from that method you can calculate the activation energy for any system. It can be 12 kilocalorie or 20 kilocalorie or 50 kilojoule like that. But in mathematical, if you just understand these things, suppose when you increase the temperature, the reaction rate decreases. Then of course you will get the negative energy of activation. So my dear young student, yes, there are a large number of reactions, and I am giving one of the example of the activation energy of simple bimolecular metathesis reaction where they are getting negative energy of activation, and it is nothing but it is applicable only for very fast reactions. So simple time dependent rate constant will not be useful. Steady state approximation will not be useful. Generally what we do, we measure that survival probability. That means when we excited this system in the excited state, so just we have to calculate the decay rate, how this is converted into the product. So that is called the negative activation energy, and again it is also published in very good paper. Now I am giving you a very specific example. As I told you that generally basically when we decrease the temperature, why are some reactions lower at higher temperature? But in a nutshell, as a M.Sc student, you can only understand that most of the barrierless chemical reactions, these are all very fast or ultra fast, and here energy of activation is negative. Now I am giving some of the specific example of negative activation energy. I am taken this example from this very important paper, and it is published in Journal of Chemical Education. You know, this journal is very suitable for the student. Journal of Chemical Education. Please always refer the article published in the Journal of Chemical Education. It is for the student thing. So some new development you can understand. It is well understood that most chemistry students at advanced undergraduate levels, that chemical reactions generally follow the Arrhenius law. Temperature dependence with positive activation energy. But it is much less widely known that rates of some Arrhenius complaint reactions are retarded by increasing the temperature. And you are getting the negative energy of activation. I am coming with one example for that. Now the first definition. What is the definition of barrierless chemical reactions? First point, that in normal elementary chemical reactions passes through the activation barrier or activation energy. But when any physical, chemical or biological reaction proceeds without the intervention of activation barrier or activation energy, that is called barrierless chemical reactions. The first definition. Second, as I already mentioned, that most of the barrierless reactions, all barrierless reactions are very fast, generally in this picosecond scale. Now, most of the diffusion control reactions are also barrierless chemical reactions. So therefore, normal kinetics will not be very useful. So we have to help the ultra fast laser spectroscopy, and no steady state condition may not be reached. What we will do? That means we will monitor the reactant population from the excited state. Sometimes it is called, in the term of barrierless chemical reaction, it is called the survival probability. So rate of change of survival probability with respect to time, with the help of some, of course, Samalyevsky equation and other things. That is the calculation. So simple time dependent rate constant will not be very useful. Now, what type of reactions are generally behave like barrierless chemicals? These are only, don't think that these are only examples. There are large number of examples are available in the literature. And there is a tremendous progress has been made for the study of theoretical and experimental observation of barrierless chemical reactions. But here I am only giving a few examples. And my basic thing is that I am following the Professor Biman Bagchi's theory in center. It is not like that this is the only theory. There are many theories available in the literature. For the student purpose, M.Sc, this is sufficient, I think. So, electron transfer reactions, photoisomerization reactions, polymer reactions, ligand binding to proteins, of course enzyme kinetic reaction, and one of the most important reaction I think you have studied in third semester, you will study in the third semester when I will teach the photochemistry, which is very important reaction, that is called the photochemistry of the vision. There is a conformation from cis to trans, different types of rhodopsin protein, vasorhodopsin, luminorhodopsin, isorhodopsin. So that is one of the most important example of the barrierless chemical reaction, femtosecond scale reactions. So now I am coming to my first reaction. Again, you have seen that is a very simple reaction, and you all are aware of these environmental ozone depletion reactions. I will not going the details of that reaction, just for sake of simplicity, for the curiosity. Yes, the why there is a negative energy of activation reaction, and of course it is ozone depletion reaction. You all know that this is the ozone depletion reaction, O3 plus X. X may be NO, X may be OH, there must be some comma. So this is the intermediate state, XO and oxygen, and it will react with oxygen, this intermediate, nascent oxygen, and there is a formation of X and O2, and then this nascent oxygen react with ozone and formation of O2. Now see very carefully that this red color is the rate determining state. You will be surprised to know that the energy of activation values, of course here they have given the EA by R, same thing. Suppose in the case of X, if I am taking the NO, so NO plus O, so it is NO2. So you see minus 210 K. Suppose in place of I am taking the OH, X is the OH. So OH 2, again you see minus 200 K. I am giving only one example. Then if I am taking Cl, comma, so that Cl and ClO reaction is minus 85 point K. What I mean to say, what I mean to tell you, that there are large number of reactions where we are having the negative energy of activations. So these are all our barrierless reactions and involve the capture of the reactant molecules in a potential wave. I will explain the things. In first part, only I will explain, only I am giving the example of barrierless chemical reaction. And though all the reactions are very simple, any student can understand, any student can write this type of reactions. Okay. Now the second example. Again, it is a very important reaction, and you know that you all know about the methylamine. You all know about the methylamine, that is yes, formula any student can understand the methylamine. Now one of the isomers of the methylamine is called the ammonium halide. Okay. Now there are the scientists, Media and Ohio, what they have done, they have studied three reactions. First reaction is that ammonium halide react with hydrogen, ammonium halide react with the water, and ammonium halide react with the dimer of water. So see, it is automatically very simple description, and you can understand these things. Normally what happened, if I have taken the reaction of, I have not given the example of hydrogen with the ammonium halide because that is not barrierless chemical reaction, but because there is a little bit activation energy is required. But when they have taken the water and water dimer, you see it is an isomerization type of the reaction. That means this formation of the methyl amine, you see that intermediate is not like that. Rather, it is like that. You see here, intermediate is minus 62 kilocalorie. And of course, the transition state, you can argue with me, so why it is 62.7 to minus 62. Of course, it is minus, it is slightly greater than that. So there is slight transition state and activation energy. Then what they did, they just changed this water, and in place of water, they have taken the dimer of the water to avoid this slight. So you see what they mean? That means when that transition state, of course, although it is minus, but that can also be disappear if the reaction with dimer is involved and the hydrogen bonded cluster shown in figure B, completely barrierless process, and you see, and any student can understand, any student can write, reproduce it without any problem. Simple, just you remember methylamine, just you rearrange it, isomer, ammonium halide, just react with these things, and you see, again, there is no transition state structure, and directly, now the question is that what we'll do, we'll measure the probability density of that excited state and that decay. We just calculate with the help of some problems. So, and again, I have taken this from Astrophysical Journals 2006. It is also old, but deliberately I have chosen because it is any student can understand this example. Now you can understand what is barrierless. At least you can understand. This is simply, I am not giving any explanation, nothing. I am just only giving the example. Another example I have taken from another research paper, the case of H2C3O isomers solving the mystery of the missing propanedione. So again it is published in, again it is also Astrophysical Journal for 2019. So here is also what I mean to say, that everywhere you are seeing that this reaction H plus CH2CO. So again and again there is no like that. But what happened? They have calculated different reactions, energy along the path of the barrierless reactions. The horizontal axis shows that the CH bond, energy length and distance. So we can call it is a reaction coordinate, or sometimes reaction surface energy and the reaction coordinates. So I am giving you the values. You see that everywhere we are getting this value, activation barrier, all reactions studied, because we are concerned about this reaction. We are concerned about this reaction. Look, hydrogen and CH2CO. CH2CCO. Oh, sorry. Here. 4. There are many types. I have not given the example, but here you see it is 264 type of things. So the reactivity of the propanol and propanediene with H are starkly different with only H. So these are an example of barrierless chemical reactions. Again, it can also easily be understood. One of the another simple reactions, it is also published in theoretical chemical account. So CH2OH, O2, OH, CH2O, just you simply add this to oxygen, nothing new. You see? Then there is a transition state. And ultimately, this is the product actually. This is also an example of barrierless chemical reaction. Now I am coming to the last example. I will not explain the theory, I am just giving the example here. In second lecture, I will give the example. Now this is the most, my favorite reaction for the student, and because it is published in, again it is a very important journal, Journal of American Chemical Society, and it is the most important reaction, and you can understand very easily. I will explain step by step. First thing is that they have taken a pyridine, you all know pyridine. So it is one of the derivatives of pyridine, N-methoxypyridine radicals. Now I will explain up to the next slides. You have seen two things. That is, one is KFR, rate constant, and here is ET. That means, and finally methoxy will be different and pyridine will be separate out. The reaction is very simple. But why it is important? Because it is of course barrierless chemical reactions, and there are two types of reactions. You can understand with this. It is single electron transfer. So it is the rate constant for the electron transfer, and second is the fragmentation reaction. Okay. Number two, that in most of the cases you have seen that there is a decay. So what we need, it is, you know, that is a electron acceptor species. So we need some donor species so that it will activate it, and then of course we will calculate their survival probability. I will explain. In second case, it is another example. Also it is published in, again it is American. You have seen that most of the time I am using the examples published in American Chemical Society journal, and it is also example of barrierless chemical. I am not giving the values. I am just only, any student, dimethyl sulfide, any student can remember, CH3, dimethyl sulfide react with F2. So there are two, and these two reactions are also barrierless chemical reactions, that is HF, CH2, CHF. Again, you can understand these things. So it is one product and it is the second product. So that product is also showing the barrierless chemical reaction. So what is my objective? Now you can understand. I am giving 4 or 5 examples, very simple type of examples, and everywhere you will find that there is no transition state, and there is no, of course there is a potential energy surface, but no activation barriers, and most of the cases the energy of activation is negative. Now I am very briefly explain this. I have taken only one reaction, and then I will start my second lecture, where is, of course, there are certain equations, certain derivations to understand the theory of the barrierless chemical reaction. Now, just I'm explaining this reaction first and then the second part of my lecture. Now you know that again it is published in Journal of American Chemical Society, and again it is very simple that this is actually donor. You can understand it is our pyridine derivative, like as I told you. So now you can understand the things, that what is survival probability and motion of the movement of that things, what is ground state and excited state. So first case you can understand that these donor, in second case I will show you that we have taken two donors. Of course it also depends upon the types of the reactions, the exothermic reaction or endothermic reaction. Here it is exothermic type of the reaction. So this donor, with the help of this, so it is converted into excited state. When I will discuss the theory of barrierless chemical reactions, I will explain that in the most of the theories is based on they are concerned about the potential energy of the excited state. But that Chakravarti's theory, they actually consider the ground state as well as the excited state. But for M.Sc student, you just understand that there is a excited state, you know, the excited state, and then of course there is a reversible reaction is also possible, but the chances are very less. So therefore I have written the minus negative electron transfer, it form a free radical and ultimately that form a fragmentation, and fragmentation a radical cation, and then of course this pyridine and methoxy and is separated. Now if I explain these things with the help of this research paper, so you can understand the first case, it is the first thing, it is an exothermic electron transfer reactions from an excited donor to a positively charged electron acceptor. The first case, because this donor is excited, donor is react with that compound is like that, positively charged electron acceptor, and the result, formation of the donor radical cation. This is and a radical. And third step is very simple, that this, because now it is a fragmentation, no role of this donor atom. So fragmentation, and it will give this new radical and neutron molecule. You can ask me, sir, why there is a less possibility of the return electron transfer reactions? Yes, that is also possible, but that is less energy. I will not explain the complete picture of this or the actual mechanism of this type of barrierless chemical reaction, because there are some theoretical explanation, there are some experimental measurement. So the complete mechanism of barrierless chemical reactions can be explained by theoretical studies as well as some experimental measurement using some diffusion control reaction. Now if you just explain again it is also I am taking from this Journal of American Chemical Society, because their explanation is very simple, because now this thing is very important, the potential energy surface of this thing, what is source and the sink actually. Now I will explain in my next lecture what is that symmetric and anti-symmetric sink and like that. So here they are explaining the most important thing is that potential energy and the distance, reaction coordinate you can call it. Now you can understand, sir, why you have written two graphs. Yes. Now they actually use two donors, and of course from this graph you can easily understand the D1 is naturally higher energy than the D2. Of course, this second example is the endothermic type of the reaction. First example is exothermic of the reaction. And this is in normal cases, it is normal distance. And so there is no very small, this reaction has to climb a very small climb here, very small climb. So the same thing, same reaction, same donor is different, but the mechanism is same. First is electron transfer reaction. Here potential energy graph is less. Second, fragmentation of the reaction, the final product. So if I just explain with the help of this American Chemical Society journal, the energy diagrams, first thing is the energy diagrams for two donors. And compound is same, that this pyridine derivatives, methoxypyridine derivatives. Now this green dash line, this is actually for the potential energy of donor 1 and donor 2, but of course donor 1 is higher. These curves have a minimum at equilibrium bond distance. You see, this point is sink point. I will explain this thing. Sink point. Sink. You can, in my next class, I will explain you that how energy is. The source point excited from there. This is sink point because we have to calculate that decay. These curves have a minimum equilibrium bond distance Rxy. D1 is stronger electron donor than T2, quite natural. And last point, the energy curve for exothermic reaction fragmentation shows a small barrier. Again, I am just showing you that. That is to claim a very small barrier. It is barrierless type of things. Electron transfer from D1 to XY to form same thing. First one is radical cation, and second is that a XY radical, and this is the actually the distance, internuclear distance is exothermic and occurs at a crossing point of the upper dash in solid curves. This point, and the fragmentation of the intermediate subsequently occurs by a small barrier. In second case, we have seen that this part. So this is a simple example of barrierless chemical reaction. To summarize, in the first part, again and again I am saying that I am giving some of the simple example of some of the barrierless chemical reaction. Now it is up to you that if you want to collect more and more chemical, more and more barrierless chemical reaction, you have to search the literature, because I have used most of the literature in late 90s or 2008, 2013 like that. And if you want to get more information, some recent articles you can be referred. Thank you very much.